Swayam Prabha. Digital India. Educated India.
So we started talking about fluid dynamical systems which primarily display temporal instabilities. And as a very important example, we are looking at flow past a cylinder. And what happens is the flow would look like this. And if I talk about flows for which if I define the Reynolds number in terms of u infinity d by nu, where d is of course the diameter of the cylinder, and if Re, to be on the safer side, I will just put it, let's say about 65 or so, then what we see is vortex shedding takes place. Okay, vortex shedding takes place, and if you take a point in the near wake along the center line and find out its time trace, you are going to see a time trace of this kind. So this is a, let's say, a streamwise component of disturbance velocity that we have. So what happens is we notice that this disturbances picks up slowly with time. Okay. And if you really find out the envelope of this amplitude, you will find that there is an exponential growth that you are noticing. Initially, you have an exponential growth, and that actually gels with what we have been talking about in the past, that the disturbance quantities would be given in terms of, let's say, their amplitude, Fourier Laplace amplitude, kind of what we are showing it by caret, and then you would have the phase given by this. But this is not truly a real phase in the sense alpha and omega can be complex. So far we have focused upon situations where alpha was considered complex, omega was real, and now we are switching our attention to cases where alpha would be real perhaps and omega will be complex. That defines your temporal instability. Now, if that is so, if omega, as I write here, I will let's say write it in terms of a real and imaginary part, and then well, let me call this a different quantity. Let's call this as S, because that's what we will be using. So let's put it like this: alpha x minus st, and S has a real and imaginary part. So this corresponds to your temporal problem, right? This is what we have done. Now, within this canopy, you can identify various cases. For example, if omega I is less than 0, then what would you have? You would have temporal stability, right? That you can substitute it here, and because of this minus sign, and there is I and I, that makes it that. So omega I negative means you will have disturbances which decay with time. And of course, this is quite well known. This corresponds to neutral case. The case that we are talking about would correspond to when omega I is greater than 0, and then we will have temporal instability. And that is what you are seeing here. In this part of the flow evolution, in the early part, this is the case where omega I is positive. Okay. And what you notice about this growth of this disturbance is that initially it takes off, and because it is exponential, so you need a very, very small trace amount of background disturbance to kick it up. And once it kicks up, then it grows exponentially. But what is noticed in this flow is that this growth is not unbounded like what your linear theory would suggest. Instead, what you see is a kind of a nonlinear saturation. So this saturation amplitude is what we called yesterday as 2AE. Okay. So basically, that's what we are talking about. The disturbance that we are seeing will have a temporal variation whose amplitude is given by A subscript E. E indicates another equilibrium state. So we start off with a case where we don't have any disturbance. Then we reach another equilibrium state where we have a saturated amplitude. And this is what you see in vortex shedding. So what you are seeing is as a vortex shedding, as I told you yesterday, it's like your fluid dynamical pendulum, right? What you see is that alternate shedding of vortices. That means what? You have some separation bubble forming here, recirculating region, which grows differentially on either side, and once it reaches a certain amplitude, that is detached, while the other one, which was small so far, takes up the throne. It's almost like your pendulum, interplay between potential and kinetic energy gives you an equilibrium state. Here also these two vortices does the same thing. So one grows, the other one remains stagnant, and when the one that is growing achieves a certain threshold amplitude, then that is shared, then the other side it starts growing. So this is thus a case where we have pointed out that here the nonlinearity is playing that role in moderating the linear growth. And the linear theory of stability of the steady basic flow will give us a spectrum of modes, okay, with velocity perturbation of this form. So what we have done is basically a Galerkin projection, right? We have split out the space dependence and the time dependence. This A of t is like what we are talking about here, right? So A of t tells you the temporal variation, and the F corresponds to those modes that we are talking about, the eigenfunctions, the modal representations of the eigenfunctions. Okay. Now, Landau, as I pointed out, wanted to propose this as a model for turbulence, because by the time we are talking about in 30s, people understood, at least people of the caliber of Landau, they understood that this whole process of transition from laminar to turbulent flow begins with an instability. And here is an example. This instability does not take you to unbounded growth by the primary instability alone. That is moderated by nonlinearity, and then you get to an equilibrium state. And now what is the state, this equilibrium state? This equilibrium state is no more steady, it's periodic. And as I told you yesterday, that there is a developed theory called Floquet analysis, which essentially studies instability of systems whose basic equilibrium state is periodic. Okay. So now if I do that, I can now study the secondary instability of this periodic state. And Landau's model was that you would have this primary instability follows by secondary instability, then you will have tertiary, and so on and so forth. All of this cascades into eventually your turbulent flow. Now, I also mentioned yesterday that this view has been repudiated later on. People talking about chaos dynamics, they talk about systems where you probably don't need to go all the way up to infinite sequence of such instabilities. A 3 or 4 stage is good enough to fill up the spectrum completely. But let's begin from how it had appeared. So Landau proposed an equation, but let's first of all look at the initial stage where we have an exponential growth of disturbance. So if I call that amplitude the jth mode in terms of aj of t, that is some e to the power sj of t, right? Now, if that is the description of the jth mode, I can take a time derivative of it and divide the derivative by aj, I get this equation. That's what your equation 3 looks like, right? This is pretty much a consequence of linear instability, right? So what is it actually? If I put this aj on the left hand side, I'm going to get some d dt of ln a is equal to sj. So sj is some kind of an exponent of the growth, right? Now, when we look at linear theory, the corresponding space-dependent function are those sets of eigenfunctions. And if now we relax the linearity approximation and use Galerkin method, then the evolution equation for the complex amplitude, that is at aj, is written in the following form. It's given like this. So what we are talking about, we are in search of a description which defines this vortex shedding. So linear path is not good enough. We must supplement it by nonlinear action. That causes this saturation. So do understand that here the nonlinearity is playing the role of stabilizing an unstable system, which is seen to be unstable in the linear mode. Now, this is basically catch-all term which shows all kinds of nonlinear action. And the nonlinear action means what? We are studying here the evolution of the jth mode. So the nonlinear action can come about because there are multiple modes. See, one of the aspects that we studied beforehand was for the linear theory, we know linearity assumption helps you in superposition. That was one of the reasons that we talked about normal mode analysis, where we studied individual modes. However, when you are talking about a nonlinear dynamical system, superposition does not hold. So each mode is affected by the other mode, and that is in a formal way has been written down in a operator form. So Nj is a nonlinear operator working on the jth mode, and that is created by all possible modes present. So AK is written, so it should be something like summed over all possible case. Now, Landau himself suggested that this is what it should be. In fact, let me confess, Landau didn't really suggest this. This came about with further refinement of Landau's model by Stuart Watson, and that you see also in the monograph of Drazin and Reed, and also the book that I have just written with Professor Poinsot. And this is a kind of a afterthought, because this tells you how the jth mode interacts with the kth mode. In fact, what Landau himself did was somewhat different. Landau said, look, if I look at the time trace, then what I am looking at is a single peak. It's a periodic state. So what does it mean? One of the mode is the dominant mode. So basically, then I really don't have to rummage through all these J's. I should be able to look at only one. And let's call that amplitude as A. And what Landau suggested was this, that A, which is the most dominant mode, is governed by this. So this part we understand comes directly from linear theory. This is the Landau's projection of the nonlinear action. And what is this? A is acting upon itself. So this is essentially what I will call it as self-interaction term, right? Now we have said that this S is the linear exponent, growth exponent. So it has a real part and an imaginary part, right? And what Landau said, that nonlinear term is multiplied with respect to a constant. This is a property of the flow that we are considering. So in this case, the flow past a cylinder. So this constant itself is complex. So it has a real part and an imaginary part. Two together is what is called as the Landau coefficient. Now, what I could do, I could take a look at that equation. If I divide both sides by A, then I get 1 upon A dA dt should be equal to S minus L by 2, and this is this. Okay. So this also could be written down in this form. You will agree with me? So if I do like this, now A itself is complex, so I could have a polar representation. So if I write A as some radial vector times I theta, r times I theta, then what happens? Of course, you can see that ln A is ln r plus I theta. So I could put it in there. So what I get from here then, I will get d dt of ln A, I will write it as ln r plus I theta. And what about S? S we have written already there, has a real part and imaginary part, right? And this I will write it as Lr plus I Li by 2. And what about mod A? Mod A is R, right? So I will have R square. So now you are actually in a position to split it into real and imaginary part. That was the whole idea of writing it in this fashion. So if I do that, what I get an equation like this. The real part will give me what? d dt of ln r then I have sigma r, and what about here? I will get minus Lr by 2 r square. So I could take away this 2 here from everywhere. I could write it here as this. Okay, so I could then write it d dt of 2 ln r. I can put this 2 inside. 2 ln r is okay. right? So what I could do, I could write this as 1 over r square ddt of r square, isn't it? Now you can see that equation, right? Now if I multiply by r square all through, I get ddt of r square is 2 r square minus LR r to the power 4. And that's your equation 7. Okay, so that's your derivation of this. It's interesting though that Landau never produced this few steps, algebraic step. He just simply wrote that the amplitude should be given like this. And of course, in his original prescription, L was just LR. And the imaginary part also now we can write it down, isn't it? Huh? What does the imaginary part give us? Imaginary part would give us here. So I can knock off the I. So I'll get d theta dt on the left hand side, and on the right hand side is omega I minus Li by 2. That's what we have written there also. Now, we do not know how Landau obtained this equation and not this, but this is how it is. There are two things that comes out. That this equation is almost like what I say in science, how subjects have developed, that first you have a key, then you go around looking for the lock, right? That's how you see how Navier-Stokes equation was written. People kept on finding out simplified cases for which solutions exist. So solutions are like key. And then you go around and see in which physical phenomena that model works out. So Landau also perhaps took that kind of an approach where he looked at this equation. This equation is what? It's a nonlinear equation, right? It's a nonlinear ODE. But the good news is this is exactly solvable. So because it has an exact solution, and that solution has a very interesting feature which can explain this saturation, is what is important about this equation. But needless to say, if you look at the phase variation is interesting. This is like your Struhal number. This omega that we are writing here is like your Struhal number that you would be actually measuring. If you put a probe here and get the signal, do a 50, you will see a dominant frequency. That frequency is of course this, right? That is this. But what about this part? This part is a very, very interesting part, because what does it say? That your actual frequency not only depends on what you get from your linear theory, but it also gets modified due to nonlinearity. And you can very clearly see this frequency is amplitude dependent. It depends on a square, right? So this has captured the imagination of many researchers, and lots of people actually, in studying this particular flow, reports results on variation of this Struhal frequency on the background disturbance amplitude, etc. And that may have its clue in this equation. So I suppose, having gone up to here, we can talk about the following, that this Landau coefficient, it's still a multiplicative constant, okay? And we do not know what kind of real and imaginary part it will have. It also depends on the sign of the real quantity, because we have written down that equation. The sign itself will determine. What is it actually? What does it say? The time rate of change of the amplitude is determined by the linear instability, but if the sign is different, then what does it do? If LR is positive, it reduces the ddt of R square. So it actually decreases the linear instability. So LR positive is the case where the nonlinearity stabilizes. But if LR is negative, you can very clearly see that it could give rise to added growth due to nonlinearity. So Landau was very much aware of this. So what he actually proposed, he was also interested on many things through this single equation. He was hoping that he will be able to explain that nonlinear saturation in case of blob body flow like flow past a cylinder. He was also hoping to solve those problems which had shown stability through linear analysis. You can very clearly see the case that this part could be negative, the linear part, right? This sigma r times r square. This could be negative. So what does it mean? It's linearly stable. However, if LR is negative and this quantity overrides this, then it will be non-linearly unstable. So flows like pipe flow, wet flow, Poisson flow, that's where maybe one would be interested in the negative LR. Okay, I will not talk about that. We do not have time, and there are not much of advancement that have gone in. It's time somebody starts looking at, with the help of DNS, they can start looking out for the Landau coefficient for some of these flows. So this is also another open, challenging research problem I can suggest to any of you willing to continue in this field. It's very interesting because this is the need of the hour. There are lots and lots of fluid dynamical systems which still evade a proper answer. So this could be the case that one should be solving for those and then get the answer. So what we'll be talking about in this case is flow past a circular cylinder, because I suppose this is a sort of a canonical problem for which many engineering discipline looks out for an answer, right? So we'll only be talking about LR as positive. We said that the instability begins as linear instability, and the first appearance of this is created by Hopf bifurcation. If you recall yesterday, I did talk about the Hopf bifurcation. So basically what we talk about, that if I plot in the parameter space, in this case, it's a simple problem. Only parameter is Reynolds number. And on this side, I'll plot, let's say, AE. And then what I said yesterday, that up to some value of RE, you'll get this kind of a thing. So where the linear instability begins, the amplitude goes almost like vertically up. So this is like 90 degree. And that is what is called as the Hopf bifurcation. The Reynolds number at which the first bifurcation occurs is indicated by the symbol RE critical, RECR. So what does it mean? That above RECR, this real part is positive because it's unstable, right? Linearly unstable. So that's the harbinger of linear instability. Now, once that happens, we do get some interesting solution. What we would be talking about, let's see, if I have this, no, I did not write this solution. Okay. We have this equation. We have this equation 7. Now, what happens is, we are seeing how the linear growth rate is moderated by nonlinearity. Now, when I reach this plateau, means what? What happens to this? d dt of a square will become 0, right? If that is 0, then I have reached an equilibrium state. So, I can put a equal to ae here. So, if I put this equal to 0, that gives me a value of equilibrium amplitude, right? And that directly comes from here. You can see from here, if that is equal to 0, then you can see there are two solutions, right? One is of course r square, another is 2 sigma r minus Lr into r square. Now, this equal to 0, and that we can talk about. And you very clearly see one of the solution is this, and that is this. So, at any RE, I have one solution that corresponds to r equal to 0, and the other solution comes from here, and that is your this. So, of course, I will write it like this. So, Landau's equation, without even solving, helps us identify the equilibrium state. But you can actually solve it. I will leave it as a sort of a short homework. It will take you a couple of minutes to solve it as a function of A. What you do, as I told you, divide by a square, and then it becomes very easy. You will be able to solve it, and you will see that the solution a as a function, mod a square as a function of t, would be a decaying function of time. So, after a long time, so initially you will get this part, but for a long time it will saturate. The time dependent part slowly tapers off. That is why Landau took this equation. So, I want you to write down this equation. If you can't get the solution, you can come back to me. I will tell you how to do it. Okay, so we talked about this, and this is what I said, that equilibrium amplitude corresponds to this case. Very interesting, right? So what you get is the equilibrium amplitude is given by sigma r divided by Lr. How is sigma r as a function of Re? I have crossed Re critical, that is why sigma r is positive. So sigma r that we are writing here should be proportional to Re minus Re critical, isn't it? Because flow will become more and more unstable, Reynolds number keeps increasing. And if sigma r keeps growing like this, what happens to the equilibrium amplitude? It goes like this. And what is the nature of this curve? Parabolic. Because you can see here, AE goes as square root of Re. So if you now go to the lab and do the experiment, all you do is you have a hot air probe, you keep measuring, keep increasing the Reynolds number, and you get this, draw this curve. And you have found out where that RE critical is, and if you have this curve, you can take any 2 points and you can obtain this. In fact, some experimentalists did it. Paul Strykowski, working with Professor Srinivasan at Yale, they actually solved this problem experimentally and tried to comment about what happens to omega r, LR, etc. We'll see what those results are as we go along. Now, I would show you a comment. I'll show you a comment attributed to Landau. He did not think very much about the ability to find out the imaginary part, that is the Strual number. He says that remains indeterminate, but we have written down the equation, so we know better now. But the Strual number also depends on the nonlinear saturation and the amplitude, but depends on also Li, right? So if I do study flow past a circular cylinder experimentally or by very accurate numerical method, and you know that we do that. We do solve equations with a great deal of care and accuracy, so we do get results, and we actually produce what these parameters could be, right? So we should be able to show that. See, as I told you, here are some excerpts from what Landau wrote originally from his collected papers translated. He wrote that the essential fact is that only the absolute value of the factor, but not its phase, are determined by that Landau equation, that complex equation that was written. He did not even write down the complex equation. He wrote only this part, this equation, this part, and he was not aware of the existence of this. That's what he's saying, that phase is not determined. The phase remains in substance indefinite and depends upon the initial condition, which are a matter of change and may cause phase shift to take any value, which is in hindsight is not correct. Here, instead, we have developed everything in terms of amplitude and phase. In fact, Landau's original paper refers to Floquet analysis. That's what we talked about, which relates to the secondary instability. And he wrote it that as RE is further increased, this periodic motion that we get, that vortex shedding, if we keep on increasing the Reynolds number, then that also again become unstable. That's what he means by unsteady, means not periodic, or the period changes to something else. So that's what he means. The periodic motion in the last sentence is the primary instability following the linear temporal instability via Hopf bifurcation. And this eventually becomes unsteady is basically the secondary instability. Interestingly enough, in 80s, Professor Herbert, when he was in Germany, he used this to study the secondary instability of flow past a flat plate. And there were quite a bit of interesting work done, and I will not go through that aspect of secondary instability of external fluid mechanics, but that is totally based on what we are talking about, is a Floquet analysis. Suppose, so the scenario is something like this, that I have a flow over a flat plate, let's say. We create a Tolman's twisting wave, and we have a parameter combination such that we have a neutral stability. So if I have a neutral stability, what I will get? I will get a periodic solution. That periodic problem is susceptible to background disturbances. And that is what was studied by Herbert in the 80s. We wouldn't have time and will not talk about it, but that is what Herbert studied following this original idea of Now, show you some bit of numerical results, or maybe I should go over to a better quality picture, but still let's try to understand what we are seeing here. It's basically numerical solution of two-dimensional Navier-Stokes equation. What we have plotted here is CL versus time, CD versus time, and what you notice that the CL versus time, it shows some kind of very high frequency oscillations. But then again that quenches, and then again it suffers that, and afterwards slowly these instabilities that we are talking about, they pick up and you get to those kind of equilibrium amplitude and the frequencies, etc. The drag also shows similar kind of corresponding high frequency oscillations, but once this nonlinearity sets in and you go to a next equilibrium state, you notice an interesting thing. The drag reduces. This almost go with the aphorism people say that nature always finds out the least energy solution, right? So it's like this. Although in a transient phase the drag goes high, but when you reach the equilibrium state, you actually again come down to a low drag configuration. So this kind of nonlinear stabilization is a kind of a nature's way of optimizing and bringing it to a low drag configuration, and this kind of periodicity is also seen here. So this is just to show you an example of numerical solution, but let me just get back to what we were looking at before and talk about what has gone on and how people have viewed vortex shading behind a circular cylinder. People have called it a Hopf bifurcation as a consequence of linear temporal instability. The above temporal instability is moderated by nonlinearity, which can be explained by Landau equation. You can read it in Landau's original work or in Drazin and Reed's monograph. Some numerical investigations have been done in mid-80s. Most of them were either Galerkin finite difference calculation or finite element calculations, and all of them in synchronicity say that this instability that you see from the solution of Navier-Stokes equation happens in the range of RE 45 to 46. This became like an urban myth, and all of us suffered because of this insistence that there is one such thing as RE critical. However, if we look at the experimental results, we find that there is no such thing as a universal RE critical like those numerical solutions investigators showed. What really happens is that different people have commented on different values. For example, if you look at Batchelor's book, he conjectures that it should be between 30 and 40. And Landau and Lipschitz actually quoted it as some 34 based on some unreported result, but it is there in Landau and Lipschitz's book. So these are what you see in textbooks, what people have been talking about. If you look at the recorded experimental data, then Kovazny reported it to be as 40, much below that 45 magic number of this numerical calculation. And this was the work that I was talking about, Strykowski's work with Professor Srinivasan, and they reported these results in late 80s, and it is something they said that it is between 45 and 46. This is an interesting result. But if you look at Roshko's original work in early 50s in NASA, he reported a value of 50. This group in Japan, they reported it a value of 52. And Tordella and Cancheri has actually shown it to be 53. But this was what yesterday we were talking about, Fritz Hohmann's work. Fritz Hohmann reported it to be 65.2, a maximum value. So if I want to talk about theoretically, flow criticality is related to the onset of global linear instability. That is what those three people claimed, and they said that this happens like this. And we need to reconcile these two viewpoints, and we'll do it shortly. So what we see as the instability reported by those numerical investigation in the vicinity of 45, let's call that as RE critical 1. And the value reported by Hohmann, let's call it as RE critical 2. Hop bifurcation actually describes the passage of a dynamical system from a steady state to a periodic state. As the bifurcation parameter, in this case the Reynolds number, is varied. So this is a nice reference. You can read about bifurcation, Golubotsky and Schaefer's book. The results of the numerical investigations mentioned above relate to study of the flow system unimpeded by noise or perturbation, barring numerical error. I think this sentence looks very innocuous, but you have to understand it, that in experimental facilities you always have background disturbances, right? Or for that matter, your cylinder is not a perfectly a circle. It can have surface irregularities. That is not what we do in numerically. But of course, when we do numerical calculations, we are subjected to numerical errors. And numerical errors, those of you know, comes in various colors and shades. So you have to think of it very, very carefully. It's not just simply saying it's truncation error, round of error. We know there are various sources of error. But we need to understand that this is a major point of departure when we try to reconcile experimental results with numerical results, because we are not talking about same things. We are talking about apples and oranges. So when we are talking about flow instability problem, dispersion error is a major problem. You see what happens. We are talking about disturbances which are growing, evolving in space and time. How is it related? It's related through the dispersion relation. That's what we have been talking about. Numerically, most of the people were unaware of how this dispersion error affects calculation. That could be a major source of error. We can actually create spurious dispersion, and that can lead to wrong spatiotemporal dynamics. And this we have studied in a great deal of care, and we have identified that developing numerical method, we must preserve physical dispersion relation numerically. This was done because we wanted to actually study the work that was done by Strykowski and Srinivasan. What they did was, if you have a cylinder, in its wake, you put a smaller cylinder. So basically, we are talking about putting another cylinder here somewhere. I don't know where it is. They did investigate. So there is this. So this is the main cylinder, and we have this. So this, we'll call it as a control cylinder. And you know what? When you put such a control cylinder, many a times, if you position it correctly and the Reynolds number is less than 100, you see vortex shading disappear. This was very interestingly found out by Courvoisier. You recall I just now showed that Courvoisier in 40s reported a critical Reynolds number of 40. He noted that when you bring in a hot wire probe to measure this fluctuation in the wake, that in some locations the vortex shading disappears. And this observation of Courvoisier was picked up by Strykovsky for his PhD thesis. They wanted to find out what is this role of control cylinder, how you can control it. And this was what we actually studied numerically. And they did those experimental studies. This is that famous JFM paper of 1990, Strykovsky and Srinivasan. They reported that. They showed not only that you can change the shading pattern by putting in a small control cylinder, you can do the same thing by putting in a heating element also. So looks like there are various ways of flow control. Unfortunately though, such flow control works only for lower Reynolds number. If you keep your Reynolds number restricted below 120, you can control it. So this is the reason that we looked at dispersion relation preservation scheme, because we wanted to control this. And we actually reported the results in this JFM paper, trying to explain how flow vortex shading can be controlled for RE less than 120 by just simply solving nominal two-dimensional Navier-Stokes equation. In Strykovsky and Srinivasan, there were some computational results presented, but they did not really consider the actual geometry of the control cylinder. They just simply found out a cluster of points where they did change the momentum transfer to mimic what is the effect of control cylinder. But the work that we had done in the 2007 paper, we did we solved the actual problem. And this is what we see. This is what we see very clearly. We explained that if we are careful, we see that lift coefficient evolves like this. You have very high frequency oscillations that is also seen in the drag coefficients. But then once the linear instability picks up and the nonlinearity saturates, then you get to a low drag value. I mean, these are not very low drag value, but they are quite significant. This is a function of Reynolds number. Okay, I think we need to talk about numerical issues later. What I would like to do is talk about what happened is this issue of nonlinear effects moderating instability and the amplitude equation. So below RE critical 1, the real part of sigma r is negative. So of course you don't have linear instability. While above RE critical 1, the flow becomes temporarily unstable in the linear sense. That would amplify velocity, vorticity field, and that you can trace it from the lift variation itself, right? Presence of the nonlinear term does not allow uninhibited growth of such disturbances. Passage of sigma r from negative to positive value across RE critical heralds a qualitative change of the equilibrium flow, and this is what is a formal definition of Hopf bifurcation, which we would be following. And this is the Landau's equations analytic solution. As I told you, you can see the time dependence comes here from e to the power minus 2 sigma rt. Now this is positive, right? So the exponent is negative. So as time increases, this quantity goes away. What is A naught? A naught is the initial solution. What is AE? AE is what we have written here, right? The equilibrium solution. So what happens? For very large time, this goes off, and this a square goes off, and you get A. So you get a solution, an equilibrium amplitude, which does not depend on initial condition. So this was something, that's what everybody thought that they should be able to do, that all experimental facility should show us a universal value, because it does not depend on A naught. So we'll stop here today. We'll start from this point on and see what can be done furthermore.